Oh my goodness. Okay. I love my job. Okay, let's get started. This is our last content lecture in structural analysis. We'll have our exam review on Friday, and we decided to go ahead and just combine some reviews on Friday for both classes. By the way, I was made aware there's a glitch on the not this class, but the 321 bonus assignment computation. I will fix that after class. So it's not happening in here, but it's happening in materials. I think I know what needs to be fixed. I'll take care of it. So, okay. In terms of the class as a whole, we don't really have much left. We just have our final homework, which is due Friday, and then the bonus homework, which is due. I'm going to make it due on Tuesday. Just so everybody is aware, the university survey closes on Friday, but I'm giving everybody here a couple extra days. In case you forget to screenshot it, you can upload your screenshot. And since our final in here is on Tuesday, I'll accept it up through Tuesday at 5 p.m. And then I think at that point, like, the class is over, and then I need to grade the finals and post and all that. Everybody get the code? All right, so let's get into our last lecture for today, which is to go through a matrix analysis of a truss start to finish. And maybe I'll like briefly highlight what changes with beams, just to give you kind of an idea. And I'll go ahead and just spoil it right now. What changes is how you handle the force vector. You can't just look at the structure and get the force vector for a beam and frame, especially if you have loads on the members. There's like a trick that you got to do. Let's just sort of recap our procedure. So on Monday, we sort of derived all this, and really the key point I wanted to get across last time is that the procedure for bars and the procedure for trusses are exactly the same. And really the only difference between the procedure for bars and trusses is that trusses, you have a couple of intermediate steps you have to add because of trig. That's basically it. So the first step is to assemble the K-matrix for the structure, and the process works the same way as before. The only thing we have to do is we have to take each matrix and rotate it. So you have to do a little bit more work to get to the matrices that you can assemble, because what you've got to do is you've got to compute your K-prime matrix, which is in local coordinates, and then a transformation matrix to get it to global coordinates. In order to compute these, you've got a couple intermediate values you've got to compute. You've got to compute the member length, the sine and cosine, but you don't need to get the angle to compute the sine and cosine. You can just use SOHCAHTOA and say adjacent over hypotenuse and opposite over hypotenuse. And by the way, I just put those two matrices here on the board just so that when we look at this here in a little bit, it'll be right here. And by the way, I'll mention two things. Oops, dropped my pen. I'll mention two things. Number one, in case anybody needs the Truss handout, I've got extras up here. Two, during the final, I'm going to give you both the bar handout and the Truss handout, so you don't need to put that on your formula. So I'll give you those two handouts. All right, once you get your K-prime matrix and your T matrix, you need to rotate, and you need to rotate by multiplying three matrices, T transpose, K prime, and T in that order. And that's what I'm going to go through today, and I'll do it in Excel just to show you how it works and whatnot. It's not hard, but the formula, you got to do a little bit of work to the formula in Excel to get it to work right. And then you assemble, okay? So you're going to assemble each of the element matrices into a big old matrix for the whole system. And that matrix can get kind of big. Again, for the problems that you all did for your analysis project, you easily could have had matrices that were in the 60 by 60, 70 by 70 range very easily. For this problem that we're going to do together, the size of the global stiffness matrix is a square matrix, and the dimensions are equal to the number of degrees of freedom in the system as a whole. So the system as a whole has 1, 2, 3, 4, 5, 6. So the K matrix for the system as a whole will be 6 by 6, okay? And a simple way of figuring that out is to just take the number of joints and multiply them by 2, because each joint has 2 degrees of freedom. It can move in the x-axis, it can move in the y-axis. So the resulting K matrix for the system as a whole is 2n by 2n, okay? Once you do that, you can assemble the F vector for the structure, and then you can and again, for trusses, assembling the F vector is something that you can just look at the structure and get, and then you solve for your displacements. And what I would say is step 2 and step 3 are really the same as they are in bar analyses. Really the only thing, you just got a little bit more bookkeeping to do because you've got more degrees of freedom, but it's not any more difficult. It's pretty straightforward. Once you get your K matrix and your F vector, knock out the rows and columns associated with boundary conditions, then collect those into a reduced K matrix, a reduced F vector, and then solve. Software loves to do that. I don't expect anybody to do that by hand. Then we basically back substitute. So we write a delta vector for the system as a whole, go back to the K matrix for the system as a whole, and do K times delta to sort of recompute F. And when you recompute F, what happens is you'll end up solving for all of the unknown reactions that you didn't have before. And we'll clear that up with our example today. In order to get the individual forces in each member, you've got the K matrix for each member, write a little delta vector for each member, and just do F equals K delta. Now, keep in mind, you're doing it in local coordinates, so really it's F prime equals K prime delta prime, and so since the little delta vector that you write is in global coordinates, you got to transform that as well. So, ultimately, though, I think you'll find this is really, really straightforward, and I think the best way of explaining this whole process is just to go through one, okay? So we're going to fully analyze this structure using matrix stiffness analysis. And by the way, when I say fully analyze, bless you, when I say fully analyze, I mean get every quantity that we've been interested in this whole semester. Reactions everywhere, deflections everywhere, forces in every member in one process, okay? And again, I'm not asking anybody to write any code, but just think like if you're trying to automate this process, if you're trying to develop a system where you can define a model and hit a little button and it gives you the entirety of the structural response, this would be the way to do it, okay? So here's the structure. So a couple things just are noteworthy. I've given you the E value and the A value, and that's the same for every member. So every member has the same E and A, and that's not necessary for a structural analysis. I mean, I could have this member made out of aluminum, this member made out of steel, this member made out of brass. I could have different properties for each member. So this is just me trying to make the bookkeeping a little bit easier. So we have 3 elements, okay? Each element is going to have a stiffness matrix that's 4 by 4, and again, I'm just going to use my plug and chug expressions right here for that, but the system as a whole is going to have a 6 by 6 system. And just to sort of make the point on later steps where we said that we could basically just look at the structure and write these 2 vectors at least before we begin, let's start off with the F vector, okay? So the F vector has, it represents the entire structure, so you have 1, 2, 3, 4, 5, 6. So we're going to have 6 terms. So I'm writing my little member codes here off to the side. And then all we do is we basically just look at the structure and write down the forces that we see. So if we look, for example, right here, 1 and 2, okay, what do we have at joint 1? We have a support reaction, right? This is a pin support. So I don't know what these forces are, so I'm going to call them R1, R2. Those are going to be the support reactions, okay? Whatever, we don't know them yet, but we'll figure them out later, okay? What about joint 2? Okay, joint 2 has a roller, okay? So this is kind of interesting. So let's talk about the roller. So the roller has a reaction in the vertical direction, but not the horizontal, right? So what I propose is that this is going to be 0, this is going to be R4, okay? Does that make sense? So we have, so think about like this. This is restrained, this is restrained. This is not. I mean, the roller can very easily translate this way, but I don't have any force. Like I don't have a 25 kip load right here. I don't have anything right there. So that load is 0, and then the reaction is R4. And as for 5 and 6, that corresponds to this. So this is going to be 60, and this one's going to be minus 80. Okay, does that make sense? Like, I'm hoping that's pretty simple, because, I mean, we've done this before with the bar elements, okay? And almost in a, I guess, a checkerboard type fashion, our displacement vector is going to look like this. So we're going to have a 0 displacement here, a 0 displacement here. I don't know what that is. A 0 displacement, delta 5, delta 6. So everywhere there's a reaction, there's 0 displacement. Everywhere there isn't a reaction, the displacement is unknown. So maybe I'll put my codes here. Just to highlight that. Okay, does that make sense? Don't worry, I'm going to pull this up here on the screen here in a second, so don't worry. There's nothing here that's on the board that you aren't going to see here on the screen. All right, if you look on Blackboard, you'll see that I've posted this. It's this PDF. It's like 3 pages long. Here's the PDF, and it goes through the system like start to finish. Sorry, 4 pages long. And I'm just going to walk through it with everybody here together, just so that everybody can sort of follow along and see what we're doing here. Okay? So can everybody see this? Does this come through clearly? Okay. So here's the truss. So I've just got the truss drawn here, and I've got it right here. One of the things you'll notice that I did on the board that I didn't quite do here on the screen is, for example, this dimension from left to right. I've got here that this is 12 foot. But here on the board, I'm not saying it's 12 foot, I'm saying it's 144 inches. And over here, I'm saying this isn't 9 foot, this is 108 inches. Because in matrix analysis, I need to convert everything to a consistent unit system because I want to be able to just use these formulas plug and chug. Okay? Now, the next thing I did is I wrote the, let me turn my little scroll on here. Okay. So the next thing I did right here is I wrote, this is my analytical model. This is the same thing I've got right here. And maybe what I'll do is just to sort of illustrate here on this image, I'm going to say that this degree of freedom, this degree of freedom, and this degree of freedom right here, these are the ones that are restrained. In other words, I've got a pin support here and a roller support here. So this one, and this one aren't going to move. Okay? This one can move, this one can move, and this one can move. But I don't know what those motions are, those displacements are yet. I got to figure that out. But I do know that delta 1, delta 2, and delta 4 are 0. Okay? Everybody okay with that? Okay. Any questions before we start going down the rabbit hole on this? Okay. Now, what we're going to do is we're going to go through the process of part 1. Part 1 is creating a stiffness matrix for every element and then assembling that into a stiffness matrix for the whole system. Now, in this handout I've got here, I've got every element figured out, okay? But what I'm going to do is I'm going to walk through a calculation with you all start to finish for one of the elements. We're going to do element number 2. And the reason I'm choosing element number 2 is because that's the one that's at an angle, so the numbers are, I guess, a little less boring, which I think will help you the most in negotiating your homework assignment. And then what we'll do is we'll go back to this, we'll do it in Excel, and then we'll sort of recap the solution as a whole. Sound good? Okay, so let's look at element number 2. Okay, so let's start off with what do we know. Okay, element number 2 goes from joint 2 to joint 3, or node 2 to node 3. Okay. So let's see if we can write down some coordinates, okay? So let's start off with x2, y2, and x3, y3. Okay, so in order to do that, we probably need to pick an origin. So I don't know, we'll pick node 1 as the origin. So we'll say the coordinates of this are 0, 0. So let's go back to basic graphing. What are the coordinates of node 2? Like if I were to get the x, y coordinates of node 2, what would it be?
144, 0.
144, 0. Okay, so this is 144, 0. And this is, I sort of have it covered right here, but 0, 108. Does that make sense? Okay. With me so far? Okay. So with this, a couple things that we can compute. Okay. So I'm going to compute a delta x and a delta y. Okay? Now, the way that I'm going to compute that is I'm going to take, if you recall in the lecture that we talked about on Monday, we need a systematic way of doing that. So the way that we typically do that in matrix analysis is we go from the higher number node to the lower number node. So what that means here is I'm going to do x3 minus x2, y3 minus y2. Okay? So that's going to be, so what I'm saying is the delta x is going to be negative. It's going to be 0 minus 144, which is negative 144, and 108 minus 0, which is positive 108. Okay? And if you want a geometric interpretation, really all I'm saying is that if I'm standing right here and I want to walk to node 3, if I want to go from node 2 to node 3, I have to go left and up. So I'm saying that the x direction is negative, the y direction is positive. Is everybody okay with that? Okay. So if I've got delta x and delta y, okay, so now I can sort of start going to work. Okay, so first thing I'm going to do is I'm going to compute the length. So how do I compute the length? Well, I just use Pythagorean theorem. Just the square root of that squared plus that squared. So okay, and so I chug that out and I get, I don't know, what do I get? But 9 to 15, was that 180? Did I do that right? I did, okay. So now I can calculate the cosine and sine, okay? And instead of, so again, be lazy when it comes to your computations. Instead of trying to get like an inverse tangent to get an angle and then take the sine and cosine of that angle, just recognize that the cosine is the adjacent over the hypotenuse, and this is the opposite over the hypotenuse. It's just polar coordinates, right? So delta x over L is minus 144 over 180, and then this is plus 108. 108. So you chug that out, and this is going to be minus 4/5. This is going to be plus 3/5. I mean, ultimately, this is a 3, 4, 5 triangle. Okay? Is this making sense? Okay. And so the only other, so let's be clear. What I'm trying to figure out, like the reason I'm doing all this math, is because right now I'm trying to get two matrices. I'm trying to get my T matrix and my K prime. So how do I get my T matrix? I need sines and cosines. Done. My K prime matrix, I need EA over L. I have L, so what is EA over L? So EA over L is, so what's E and A? E and A is 10,000 and 5.4. L is 180. Okay? So 10,000 times 5.4 is 54,000. 54,000 over 180 is a nice 300. Okay? Does that make sense? Okay. So just to sort of reiterate those computations in Excel, I put together a nice little Excel sheet right here, and so I have x3 and x2, y3 and y2. So I calculated my delta x and my delta y. So I could say, all right, let's calculate L as the square root of that. There's my L. My C value is that. S is that. EA over L is that. Okay. Everybody with me on that? Okay. So I'm going to zoom out maybe just a little bit. All right. So let's see if we can write our two matrices. So let's do K prime. So we'll call this K prime 2. And how big is K prime? It's 4 by 4, right? Now, K prime mostly has zeros in it, right? It's got a bunch of zeros in it. So I'm just going to fill it up with zeros for now. Then and then what do I need to change? I need to change this term, this term, this term, that term. So would everybody agree that that's what K prime is going to look like? Everybody agree with that? That's just going to be EA over L minus EA over L minus EA over L, EA over L. Just this matrix right here. Just this one right here. Okay? Now, my T matrix, I'm going to put this down here, is also going to be 4 by 4. And it's going to look like this, right? It's going to look like this. So the diagonal is going to be C's. So the diagonal is all these cosines. So okay. This top and bottom grid are zeros. I know I'm doing this in a different order, or a unique order. Okay. Now be careful with your signs. Okay. This one, this term right here is S. This term is minus S. Okay, so just be careful with that. This is S. This is minus S. Okay, so if you do this correctly, like at least for this problem, the T matrix is pretty much negative across the board except for that term and that term. Those are the only ones that are positive. Everybody with me on that? Okay. Sound good? All right, now, before we start figuring out our K matrix, I want to do something right here, okay? And what I'm going to do is this, okay? And I want to see if everybody's following along with me on this. So I'm going to take this cell, this, and this. We'll make them red. And I'm going to do this. All right. All right. Does everybody see why I'm doing that? 3, 4, 5, and 6? Keep in mind, we're looking at element number 2. This is element number 2. Okay? So element number 2 connects to this joint and this joint. So what I'm doing is I'm writing the degrees of freedom associated with the structure as a whole. And the reason I'm doing that is because when I assemble, that's where these would go. Okay, everybody with me on that? Sound good? Okay, now, so here's the fun part. Okay, so how do we calculate our K matrix? We have to multiply 3 matrices side by side. We have to multiply T transpose, we have to multiply K prime, and we have to multiply T. Okay? Now here's the thing though, in Excel. Okay, in Excel, so does anybody remember the formula that we use in Excel to do this? It equals what? M mult. Okay?
M inverse.
M inverse will solve the system as a whole. No, it's okay. Here's the point I want to make. Okay, M mult in Excel will only multiply two matrices. So you can only multiply like M1 and M2. Okay, but what we want to do is multiply three matrices. Okay, so let me show you how that works. All right, so I'm going to be a little lazy. Let me zoom out a little bit. I'm going to just copy this down here and get rid of all this. Okay, so my answer is going to go here. This is going to be K2. So watch this. Okay, so I'm going to put my formula. I'm just going to put this right here. All right, so let's see if we can build this formula together. Let's see if we can build this. So let's do the first two. Let's do these two. So how would we multiply these two? We would say equals M mult of what? Matrix 1 and matrix 2. What is matrix 1? Matrix 1 is the transpose of that and that. Okay? Okay, so does everybody see what I did? Right? So this right here would be multiplying the first matrix and the second matrix. Okay? But I need to multiply three matrices. Okay? So what I'm going to do is I'm going to take that whole product and multiply it again with T. Does everybody see that? So I'm doing basically M mult twice. Okay? So
what does transpose mean again?
okay. So transpose means to do this. Okay? So whenever you have a matrix, you're just taking it and reflecting it about the diagonal. Okay? We're doing that here, okay, because transformation matrices have a really peculiar property. If you transpose them, it's the same thing as inverting them. That only happens with transformation matrices.
Okay.
Yes?
Could you not also just multiply two of them together and then do the product of that as well as the third one? Or would it be like completely different thing?
Well, no. I mean, you're saying do it in a separate region. That's fine too. I'm just doing it all at once.
Okay.
Yeah. So can I erase all this? Has everybody got all this? Okay. So here's what I'm suggesting, and here's what you're suggesting, and I'm saying they're both the right answer. Okay. So here's what I did. What I did is I said, okay, let's do M mult of the transpose of T and K prime, and then M mult of that and T. Okay, that's what I did. What you're saying is do this, get an answer, and then multiply that times T. That'll work too.
Okay.
Either one works. Okay? But when we press enter, we should get something like this. Okay? You'll know that you've sort of done this right, at least for, so whenever you have a matrix that's at an angle, or a member that's at an angle, like every term should have a value in it. You shouldn't have any zeros. So if you've done this and you have a member that's at an angle and you've got zeros in here, something's wrong. Okay? So there's a couple of other checks that you will know, or at least you'll have an idea that you've done this right. Check number one. If you add up each individual column or each individual row, the value is 0. Like this plus this plus this plus this is 0. This plus this plus this plus this is 0. Row-wise, that plus that plus that plus that is 0. 0. So on and so forth. Okay? The other way that you'll know that this is right, stiffness matrices are symmetric. Okay? What does symmetric mean? Let me ask you a question. If I were to take this matrix and transpose it, what would I get? This one. If I were to take K and transpose it, what would I get?
Same thing.
You get the same thing. Stiffness matrices are symmetric. K equals K transpose. So I'm giving you checks to make sure you've done it correctly. Okay? You look like you have a question. No. Anybody have a question though? Everybody okay with this? Oh.
Wait, sorry, just real quick, that's still, it's malt and then end malt?
You're doing it twice, yes.
So wait, is the first one to be end malt as well, or just malt?
So, well, they're both end malt.
Oh, okay.
Yeah. Whoops. Think about it like this. Let me do it like this. Think about it like this. Okay. Think about it like this. Okay. This is an execution of end malt. Okay. This is a separate execution of end malt. Does that make sense?
Yeah, yeah.
So, this is basically what you're doing, is you're doing it twice. So,
Thank you.
oh, I don't need that box there anymore. Okay. Sound good? It's a lot easier in other programming languages, by the way. I didn't say that. It is. Okay. All right. Is everybody okay with this? Everybody okay with the general idea? Okay. So, let's go through this problem a little bit more systematically. Okay? So, now, we did element number 2. I want to do the whole problem. So, I'm going to walk through the whole problem with you. Okay. So, first thing we have is our nodal coordinates. So I have, we've already figured that out. I just wrote element number 1, or node number 1 is 0, 0. Hold on. So what do I have here? So what I have here on this page is, see how I did element number 2? See how we did this one together? We did delta x, delta y, the length, sine, cosine, this. So if you can do that for element number 2, well, then you can do it for element number 1 and element number 3. It's just different numbers, right? Just change the numbers for the joints that you're looking at, and it's the same process, okay? So you end up getting like an EA over L of 375 for element number 1, and an EA over L of 500 for element number 3, okay? So I went ahead and did that for element 1, 2, and 3. And then I also went ahead and wrote my global F and delta vectors, which is the same thing I've got right here. Okay, so once I have that, the process becomes pretty straightforward. So what do? I do this. Okay, so what did we do together? We as a class together did this middle one. Okay, so what is this middle one? We have K prime, which was this. We have T2, which was this. So see the 4/5 and the 3/5. And then T transpose K prime T gave us that. And that's exactly what we just computed in Excel. Okay? Now, I did the exact same thing for element number 1 and element number 3. So let's take a look at what happened, because I think that it's really interesting to see what happened, especially as you go from local to global. So take a look at element number 3. Element number 3, take a look at this. This is the local stiffness matrix, and then this is the global stiffness matrix. Does everybody see this? So this is local, and this is global. What happened from local to global? Well, really what happened is, if you look at the transformation from this to this, it's almost like the x and y terms flipped. Does everybody see that? So like, this is like xy, xy, and this is like xy, xy. They sort of inverted. Why did that happen with element number 3? This is element number 3. Element number 3 is not going left and right, it's going up and down. So what are we doing? We're just flipping the terms. Okay? Does that make sense? See, like, if we're looking at this element, degree of freedom 2 and 6 are along the axis, right? But those locally are the y terms, not the x terms. That's sort of what happened. Here's something else that's kind of interesting. Look at element number 1. Here's the local, here's the global. It didn't change at all. Why didn't it change? Well, this is element number 1, right? The whole point of this transformation, nonsense is to rotate the elements such that the local orientation matches the global coordinate system. But element number 1's already going left and right, right? Think, what does the x-axis look like for the structure as a whole? It starts here, goes that way. Here's element number 1, lower number node to higher number node. It goes this way. So there is no difference between the local stiffness matrix and the global stiffness matrix for element number 1 because the coordinate systems are parallel. Okay? Does that make sense? Everybody okay with that? Now, let's look at this. Okay, so what did I do here? This is assembly. Okay? So all I'm doing here is I'm taking each matrix, I'm putting the terms where they go in the matrix as a whole. So if I look, for example, at element number 2, this is 3, 4, 5, 6, 3, 4, 5, 6. Put the terms there. Everything else is 0. Element number 1, 1, 2, 3, 4. 1, 2, 3, 4. Everything goes where it goes. Everything else is 0. Now, this is kind of interesting with element number 3, 1, 2, 5, and 6. 1, 2, 5, and 6. You sort of have this, like, checkerboard pattern where you're only putting stiffness terms at the end. But again, element number 3 only contributes stiffness here and here. It doesn't contribute stiffness there. So what do? Put the terms where they go, add them up. And that is your stiffness matrix for the whole system. We have a stiffness matrix for the whole system. We have a force vector for the whole system. We have a delta vector for the whole system. We're ready to get to work. How do we do that? We do this. Okay? So this is the system that we have as a whole. We knock out the rows and columns associated with the boundary conditions. That's 1, 2, and 4. So 1, 2, and 4, 1, 2, and 4. This is the same thing we did with bar elements. No difference. Same idea, right? 1, 2, 4, 1, 2, 4. And so we have this sort of like smaller 3 by 3 matrix here, smaller 3 by 1 vector, smaller 3 by 1 vector. We can take this system, plug it into the wonderful world of Excel, just invert this matrix, multiply that inverse times that vector, and we get those displacements. And boom, there we go. So I propose that this displacement is 0.16 inches to the right. This displacement right here is 0.42 inches to the right. This displacement right here is 0.07 inches down. Done, right? It's that simple, okay? There's our displacement for the structure as a whole. The only thing we have left is to back substitute. So how do we back substitute? Well, go back to the big old K matrix for the structure. We now have the delta vector for the structure. K times delta, we get this. Now, this is a nifty little check that you can do in matrix analysis, because if I take this K matrix, these deltas, multiply them, I get this. Let's go back to this. This is what we wrote down before, and here's what we computed. So what do I have? This number, this number, this number. Those I didn't have before. Those are my reactions. But what about the other numbers? 0, 60, minus 80. 0, 60, minus 80. So if you do this correctly, when you recompute your F vector, everything that was there before should show up again. The whole reason for doing this, though, is so that you get your unknowns. What is this negative 60? The horizontal reaction here is 60 kips to the left. What is this 35? 35 kips up. This is 45 kips up. But think about it. I mean, look, this is 60 kips to the right. This has to be 60 kips to the left. 80 kips down, 35 and 45 up, 80 up. That's what's going on, okay? The only thing left to do is to get the individual forces in the member. I mean, think about where we're at right now. We've got the reactions everywhere, the displacements everywhere. The only thing we don't know is tension or compression, tension or compression, tension or compression. So how do we do that? We write a little delta vector for each element. Just put the unknowns that we've already calculated where they go. Plug and chug. So we have our K primes from before. We have our transformation matrices from before. We've got our deltas that we just figured out. And all you have to do is F equals K delta. You just have to rotate it. And look at what they look like. Take a look at this, this, and this. Remember what we said in mass tan is that you can take the second value, and if the second value is positive, it's tension. If it's negative, it's compression. Same story here. I proposed element number 1 is experiencing 60 kips in tension. Element number 2 is 75 kips in compression, 35 kips in compression. And that, ladies and gentlemen, that's it. We're done. I mean, we figured it out. We've solved everything in the structure. We have the displacement everywhere. We have the reactions everywhere. We have the force in every element of the structure. Hit print. It's really not that hard. That is matrix analysis in a nutshell. I'm going to take a step back. Yes?
So, I understand like this whole process. I think I'm more like thinking ahead for.
You're not going to have to do the whole thing on the exam. Okay?
Yeah, but like how would that be on an exam without Excel?
So I might ask you info about pieces of it.
Okay.
But I'm not going to make you do the whole thing on the exam.
Okay.
Don't worry. Don't worry.
And so like we wouldn't have to like multiply two matrices.
No.
without Excel?
No, don't worry about that. Don't worry about. I'm not going to make you do anything that you cannot computationally accomplish with any old calculator. I promise.
So if we just know like how to do the two papers that you're gonna give us, like do you think that's fine?
Yes. Yes. I promise. This will not. If you understand this process, you're going to be just fine. Trust me.
Do you think before Friday, or like maybe on Friday, we could go over maybe like what a problem like that would look like?
I've got to think of one. That's not the one I asked on the exam.
You can always just change the numbers of that one.
We're not doing that. We're not doing that.
Why?
What? Okay, I thought of one. That's not on the exam, but is emblematic.
Is it off the dome?
Off the dome. Off the dome. Okay, I thought of one. Okay. Do you understand this? How, if we're taking, let's take element number 3. So element number 3 goes 1, 2, 5, 6. Okay? So if I'm assembling that for the structure as a whole, I have this empty 0 by 6 by 6 matrix, and I put the terms where they go. So this, and this, and this, and this, etc. Do you understand how you could get from here to here? That has nothing to do with Excel, that has nothing to do with matrix manipulation, but it's still relevant to the process of matrix structural analysis, the idea of assembly. Does that make sense? That has nothing to do with solving some ridiculous system. But if you can do that, you understand the process. There's an off-the-dome style question, okay?
Great, thank you.
Like taking an element and assembling it.
Okay, yeah, that's straightforward.
There. That's the best. That's the closest answer I can give you without going too far. Let's just take a look at the exam, you know. And I'm not doing that.
No, yeah, that's
Forget
fair.
the question.
I guess I understand.
I would forget the question.
What?
Non-intentionally.
What's
What
that?
if we just like promise to forget the question?
I forget it accidentally, I'm sure.
My PhD advisor in grad school, he a while back, the steel manual used to have example calculations in the steel manual. Like, you would be in the section of the manual on beams, and then there would be an example, hey, by the way, here's how to use these tables. And this one year he put that problem on the exam. Nobody noticed it. It was solved out. Like, all you had to do was turn to that page and the answer was right there and nobody saw it.
Nobody?
Nobody.
Not even you?
What's that?
Not even you?
I was the TA. No, I was the TA. Like,
You just tell them, hey, flip the page.
what's that?
I would've just told them to flip the page.
It's being dishonest, guys. Mike's not dishonest.
He was a good TA.
My advisor, he was a funny guy. Like, we were doing this night exam in steel design once, and this one student, he was just sitting up there, and I think he like sneezed or something or coughed or something, and the student shushed him, and he went. And for the next like hour, he would just like, oh, sorry, to knock stuff over. So I had to leave the room because I was getting ready to start laughing. So he thought that was hilarious. So random anecdotes. Okay, did this make sense? If you all I can tell you is that if you understand this process, I promise you, this exam is not a time crunch. It's not. Okay, I promise you. I'll say one other thing. Of the 3 topics that are on the exam, which is masthead, matrix analysis, and influence lines, I think the most challenging is the influence lines. That's just me. So, I got 2 questions here. Yes.
Are we gonna use the equation function on our calculators, or are we gonna need that as a matrix thing?
At most a 2 by 2, nothing more than that.
Okay.
No, nothing more than that. And I said at most.
Oh, I'm just doing for the math one part, we don't get those handouts, right?
What handouts?
The, like, tutorial. math.
No, but you've got a formula sheet too.
Yeah, no,
You
I
got,
just wanna make sure.
you got a formula sheet. Everybody's getting nervous about the exam. Don't get nervous. It'll be fine. What?
It's a little bit important.
Oh, it's just your entire life all hinging on the process.
Yeah, I mean, it's no big deal.
It's no big deal, you know.
I only have like a 90.
All right, everybody got everything? All right. I'll see you on Friday. Friday, not Thursday, Friday.
Mike, what are you doing tomorrow at 12:30?